Okay, we finished our lecture on the radial flow. And you remember when we are in the radial flow, we were able to estimate the permeability and the skin factor, right? So today we are going to talk about wellbore storage. And wellbore storage is something you have to deal with. It basically tells you nothing but the wellbore, but you have to deal with it. And the problem with the wellbore storage, when you run a pressure build-up test, it prevents you to get information about the reservoir. So what can be the problem about wellbore storage? I mean, if you have a tight gas well and you are running a pressure build-up test. No. Okay, let's say you have a tight gas well and you want to fracture it, but prior to fracturing, you want to run a pressure build-up test. And then you run your pressure build-up test and you are looking at your data. And you see nothing but wellbore storage. And usually wellbore storage takes sometimes it takes like 2 or 3 days, sometimes it's 1 month, sometimes it's 3 months. And that's something you have to deal with it. So we have 2 types of wellbore schematic you see here. The first one is the fluid-filled wellbore case. As shown here. And here is your surface pressure readings, and this will be your pressure at the valve sand face. Okay, and this is the second wellbore schematic, and this is the rising or falling liquid level. And each case you are producing only from wellbore. So there is no reservoir information in these 2 cases. And then you are producing from here, sand face. This will be your rate at the sand face. And this is your rate at the surface. So once you shut the well in, it depends on where you shut. I mean, if you shut from the surface, then the wellbore storage domination will be very long. But if you shut from, I mean, if you shut at the sand face or somewhere here, then you may not see wellbore storage domination for a long time. It may take a shorter time. Okay? And also, since I said you are only producing from wellbore, tell me how to derive this equation. Okay, any ideas? So we are only producing from wellbore. So just think it like a tank. So you are producing from a tank. So can you guess a flow regime for that? We see that before. Okay, you remember the pseudo-steady state flow regime, right? When you are in the pseudo-steady flow regime, I mean, it's like a tank, right? So to derive this equation, all you need to do is write a material balance equation. And it will be mass in minus mass out is the accumulation in mass. So if you do that, then you end up having this differential equation. And here, this is your sand phase rate. This is the rate here. And this is your rate at the surface. This is the rate actually you know. You don't know the sand phase rate. Always you know the surface rate. Now this is the formation volume factor, we already know it. And this is the pressure at the sand phase. And this is the pressure here at the surface. So now we have to define this term. And what is this term? This is called the wellbore storage coefficient. And this is the ability of the wellbore to store fluid. So if we take this as this is called the wellbore volume. So this is in barrels. And this is the compressibility. So our wellbore storage coefficient will be barrels per psi. So in other words, it means what is the change in volume with respect to change in pressure. So it's like something, you remember the compressibility equation? Okay. So basically if you start from the compressibility equation and then solve for the volume change, then yes. Yeah, that's right, sorry. So if you start from the compressibility equation, solve for the volume change, then you end up in the definition of the wellbore storage coefficient. Now this is the other definition of the wellbore storage coefficient with a rising or falling liquid level. Okay, so let me summarize. We start from the material balance equation and then the definition of the compressibility, and then when you work out the math, then you end up having this differential equation. And using this differential equation, we are going to solve for the pressure change during wellbore storage domination. Okay, and now let's do that. Yep.
What's the general meaning of like wellbore storage coefficient? What does it result in?
You are asking for the definition of the wellbore storage coefficient? I mean, it's the ability of the wellbore to store liquids or fluid. Okay? So it's, I mean, look at the units. CS is reservoir barrels per psi. So it's like, what is the change in volume with respect to change in pressure? Okay? So if the coefficient is very low, then you don't see wellbore storage domination too much. And we'll see this in the next slide. Okay. Now let's derive the pressure change. Okay, so this is our differential equation. What I did here, I just neglect this. Okay. And then now I'm going to separate. And then I'm going to call this as the wellbore storage, as the slope during wellbore storage domination. And then it's going to be T equals to wellbore storage times Oops. No, it's the rate. I mean, okay, so if you remember this, this will be your Q. And what is the sand phase rate look like during a drawdown? Okay, what's the difference here? The first, okay, this is the first sand phase rate. And can you compare this according to the wellbore surge coefficients? So, okay.
The third one, the greatest one?
What?
The third one is the greatest one?
That's right. So also this means that in the third one it has the most wellbore volume. And I think I lost the derivation in here, but I mean, basically during the wellbore surge domination, bless you. During the wellbore surge domination, your pressure trend will simply be a linear trend. So it will look like this. Just a straight line. And the slope of the straight line will be your A&M wellbore surge coefficient. Okay, and similarly for the build-up, when you shut the valve, is Q. Goes down and becomes 0. No, at the build-up and what? No, I mean for the, okay, I didn't hit your question. What's that?
So that the dashed line, is that Q of the surface or Q of the same thing?
Well, okay. Oh, sorry, I already did the build-up. Now I am doing the drawdown. It's reversed. So, okay, this is for the build-up actually. No, actually, that's right. This is for the drawdown, because during the drawdown you have a constant rate at the surface, okay? But in the build-up, but if you shut from the, if you shut at the sand face, then it's 0. But at the surface, you still have a rate, okay? And when you look at the pressure trend during the drawdown, the pressure at T equals 0 will be the initial pressure. And here we are drawing the pressure with respect to the delta T because we are in the build-up. So here at delta T equals 0, then we will have the pressure at delta T equals 0. Yep.
How is the MWS constant if the Q sand phase changes through time?
No, but we are looking at the surface rate. So I mean, you don't know your sand phase rate.
But didn't you define MWS?
Okay. I mean, I have to redrive it. Sorry, I need to go back. Okay, everybody got this? Okay, in this derivation, I was going to do that, but I mean, I just deleted. Okay, what happens is you don't know this actually. So all you have is minus QB equals to 24 CS this. Okay? I mean, if you, so dt equals 24 CS okay? So let's take the integral from 0 to t, and this is from pi to PWF, right? So it becomes t equals to minus 24 CS QB right? So if you take this and then bring it to the left hand side, then it will be QB divided by 24 CS times T PI minus PWF, right? So the equation for PWF, then we have PWF is equal to PI minus. So now I am going to call this the N-Wellbore storage coefficient. N-Wellbore storage coefficient N-Wellbore storage slope and times T. Okay? And now this is your straight line equation. So this is for the drawdown. For the build up, then this will be PI will be PWF at delta T equals 0 plus N-Wellbore storage times delta T. Okay? So you have two different equations. For build up, the slope is negative, it goes down. Sorry, for drawdown, slope is negative, it goes down. For build up, slope is positive and it goes up. Sorry? No, I didn't neglect it. The only thing is we don't know. We don't know Q sand phase because we can't measure it.
So you can just cross it out?
Well, no, actually. You cannot cross it out, but what you can do, you can solve for it.
Well, is Q sand phase constant? It's not.
No, Q sand phase is not constant. Q is constant. Your surface rate is constant. No, slope term does not have anything to do with the Q sand phase. Sorry. Okay. Okay. Let me go to the notes. Okay, here's the thing. Okay, everybody can see the equation and the plot on screen? Okay, we are in a drawdown test, right? And at the early time, our sand phase rate is 0 because you are only producing from the wellbore. Okay, at the sand phase, the Q is 0. Okay, so since the Q is 0 at the sand phase, this becomes 0. Is it clear now? So during the wellbore storage domination, you are not producing anything from the reservoir. You are only producing from the wellbore. So the sand phase rate is 0. And if you look at your rate profile here, this is your rate profile. And this is where you are in during the wellbore storage domination. Okay? Is it clear now? So here is the wellbore storage domination. And tell me where you are in here. You are at the radial flow. Okay? Okay, so once again, when we look at the wellbore storage domination, all we see is nothing but a straight line during wellbore storage domination. For the drawdown case, this will be a negative slope, but for the build-up case, this will be a positive slope. Here. And from the slope, what you can find, this is your slope, this is your slope. You can only find the wellbore storage coefficient during wellbore storage domination. Okay, so before solving for the complete thing, let's remember up to now. For the radial flow, what we find, when you look at the data, how you understand you are in the radial flow? Okay, so So if we are in radial flow and if we plot the data, the pressure versus the logarithm of time, all we see is nothing but a straight line, right? But if you plot the pressure versus not the logarithm of time, but if you just plot the pressure versus time and you see this, what do you understand? If the time is early, then you are in wellbore storage domination. Okay? During early time, if the pressure with respect to time is linear, then it is wellbore storage domination. And if the pressure is linear with respect to logarithm of time, then this is the radial flow region. And we call this middle time. Okay, so this is the way to look at the data. But in fact, in reality, your data will look like this. So now I am going to plot all the data with respect to pressure, and this will look like. So here you need to differentiate the flow regimes. Okay, and these are the ways for us to look into the data sets. And if you plot the pressure versus the logarithm of time and you see the linear trend, then you are in the radial flow regime. And if you plot in a Cartesian plot and you see the linear trend, then you are in the wellbore storage domination regime, and this is the early time usually.
So that's early time on the left and then going to middle time on the right? When you say wellbore storage domination, be early time, right?
Yeah, early time. Okay, and I'll continue on wellbore storage full solution on Monday. And now it's time to quiz.